So we're going to kind of break this apart, but these are all Milky Ways. These are all our Milky Way in different wavelengths. And notice the way that they're arranged is up here at the, well, maybe you can't tell, but here we have the longest wavelength at the top. I think that might be radio. Longest wavelength. And down here at the bottom we have the shortest wavelength. Okay. All right. So kind of near the middle there, we have the visible one and infrared. Okay, so as you go up, you're getting longer wavelength. And the things emphasized at the bottom there is that notice it looks a lot brighter in infrared than it does in visible. Because those dust lanes I said, actually, those dust lanes, they hide visible light, but they don't hide infrared energy. So infrared energy goes right through those clouds. Okay, so now going shorter wavelength than visible, these are X-rays. So kind of emphasizing, this says hot gas above and below our disk. So this blue is our disk, and there's hot gas above and below. Then going up to the top there, that's radio astronomy. And notice down here it says, what's so cool about radio astronomy? It can detect that hydrogen, remember hydrogen, and then you get, it cools down, then you get molecular clouds, and then you can get star formation. So looking at this 21 centimeter wavelength, actually, you can kind of get the precursors for where stars can be born. And then a little bit shorter than the 21 centimeters, still in radio type wavelengths, you can look for the molecule carbon monoxide. CO, that's what we try to detect, okay, like in our houses. Okay, an indication where stars can be born. Okay. And then, of course, we said this is visible, and this was infrared, and this is a little bit longer infrared. And we have one more down here. So if this is X-rays, this must be gamma. And it is. Okay, so now gamma is the shortest wavelength. It's the most energy. And actually, this is where we're seeing stuff blow up. So like this says, we've been talking about the two different types of supernova. Okay, but this is kind of a hot spot. And we are right about here-ish, does that seem right? If this is our galactic nucleus, this is our central bulge. About half of that. Okay. So early on in this course, we talked about nebula, and I think you might have even had a term in Unit 1. So nebula is just basically a gas out there. A gas where not associated with a star. Stars can be formed in nebula. We said that actually stars as they die, planetary nebula, stars can give up nebula. So there's different types of nebula in that sense. Ionization nebula simply means that there's some sort of energy that is actually exciting the electrons in that gas, in that nebula. So in order for an ionization nebula to occur, you need some sort of energy. Okay? And the energy for ionization nebula is basically hot stars are kind of glowing, exciting that gas. Not entirely dissimilar from using electricity to excite the gas in our tubes. Reflection nebula, a little more subtle. Okay, reflection nebula simply you have a star shining. You can see the star kind of shining behind that cloud. Doesn't it kind of look like if you're in fog, like it's a foggy night, and you kind of see stuff smeared out? Okay, the light tries to get out or get to you, and it's kind of scattered within the fog. That's what reflection nebula is. Okay, so actually, I wished I would have said, I'm going to add to this slide, this is an example of a dark nebula. And remember, there's a lot of things in astronomy, naming things. There's a lot of things that have proper names. And so the Horsehead Nebula, there's only one Horsehead Nebula. Does it look like a little chess piece? Yeah. So it's an example of a dark nebula. Now, I've never had a telescope, because we should be able to see this if you can see Orion's Nebula, you know, from in the sword portion of the constellation. You're in the vicinity of seeing this one, and I've never had a telescope that has that resolution to see this. So, but there it is. Okay. So we're going to the next few slides kind of differentiate between kind of the disk and the halo region. There's some kind of differences. In the disk of the Milky Way, like in the disk of the other galaxies we're going to talk about next week, okay, we have star formation. So what's important there is star formation in the disk. So guess what we have in the halo? No star formation. Okay. In the halo region, we have, I have a slide to say as much, but basically they're kind of older stars. These are globular clusters, okay, and no new star formation. They're like old people housing, you know, they are. They're like off on their own. Don't even come here for trick-or-treating, because we're not doing it. Yeah. So this actually is a face-on photograph of not the Milky Way, but the Whirlpool galaxy. Again, Whirlpool being a proper name. And we learn a lot about our galaxy by looking at other galaxies. Okay, we were kind of talking about how does science know anything, and this is one of our clues. So it's a spiral galaxy. Ours we think is a barred spiral galaxy. But in the arms, actually, in general, in any spiral galaxy, in the arms you see a lot of star formation, and you can kind of see the kind of dust lanes between the major arms. That's dust, okay? Kind of gas clouds. So what this is talking about is if basically from the nuclear bulge you kind of have these spiral arms of stars. You're like, how in the heck did you get a group of stars to be like that? A blank, another group of stars, a blank, another group of stars. The Milky Way has, we think, let's say maybe 2 major arms and 4 minor arms. And to get the stars to be born like that, basically what works well is what this is describing, kind of a compression wave. Because remember when we talked about fragmentation, kind of formation of stars, that helps to kind of get the little protostar started. Okay. So, halo stars. Comparing the disk stars and the halo stars. So we said just a minute ago that in the disk you have new stars being born. This is like the family zone, okay? And then you have the whole people region kind of in the halo. Maybe globular clusters, but they're older stars. So one of the things that I'm hoping you guys get a grasp on is here where we have kind of the younger stars. Okay, they're younger and they are, how do I say? Well, they're blue. What do we know about blue stars with regard to mass? Low mass or high mass? High mass, very good. These high mass stars are kind of turning over fast. Okay, blowing up. Supernova, they don't go out with the white dwarf, okay? So you have a lot of turnover here in your disk. Okay, so the deal is, with a lot of turnover, you have a lot of recycling going on. And so I know it doesn't seem like a lot, but you have lots. You have lots of heavy metals. 2% doesn't seem like much. Honestly, Our star has, the sun, has the element Fe in it. Our star, the sun, has iron in it. And so just because of that, we know actually it came from a star that went supernova and it was reassembled to become our sun. It wasn't from just the plain old hydrogen from the Big Bang. It's a recycled, it's a second generation. Okay, so these guys, okay, these are actually what I'm going to call in a minute a certain population. If you compare that up here, these are low with regard to heavy elements. And so actually, we're going to say very little recycling. Get off my lawn. Okay. Anyway, very little recycling. So here now is where I get to tell you, and we do this in science more than we should, kind of the flip-flop when it comes to naming things. These guys in the disk, we actually call population 1. These guys in the disk, they are young. Okay, population 1 are young. We call them metal rich. I know, again, 2% doesn't sound like much, but it is. Okay. Where are they located? They're in the disk. Metal rich. So, in contrast to that, up here, we call these metal poor. Poor things. Metal poor. And they are population 2. And actually, these are, I'm just going to go ahead and say grandparents. I don't know if I'm saying that right, but they're like the old generation. And these are like generations in the disk later. Okay, but we call them population 2. To me, it seems like that should be population 1. See? I can remember when I was first getting ready to teach this, and I was like, I had to read that, and I reread it, and I'm like, dang. So here's the deal. A few years ago, it's been maybe 3 or 4 years ago, I read an article about population Roman numeral 3. I'm like, really? Okay. So if population 2 is like the first generation of stars, what's population 3? And it's like even more metal poor than population 2. You know what I'm saying? I don't know. So somehow you got to get that turned around in your mind. All right. The term spheroidal, I can't pronounce that. Okay, anytime you hear spheroid, you know what I mean, like a sphere, spheroidal, kind of think halo region. Okay. And the disk population, they are the newer stars, they are the recycled stars, they're the fast livers, they're the blue ones. Okay, and they recycle themselves. The ones in the halo region are kind of like, I've done that. No new storm stars are generally being formed. So this gets a little bit to maybe what Tina was asking, and we'll be talking more about this actually when we talk about the Big Bang. But our galaxy probably formed from a big cloud, because if you figure, we say our star formed from the solar nebula, which I think is pretty big. But something that's going to form our galaxy of stars, it's got to be even bigger. Okay. Had a little bit of spin to it, and as the spin made it flatten out and rotate faster. Okay, and as it aged, it allowed for stars to be born. More massive stars were born first, and then they kind of settled down a little bit in size. Did you get that? Okay. And then here's where I say, or actually your author said, warning, that's oversimplified. So the globular clusters then, and actually we're going to talk about this, I think I kept it in my notes when I talk about finding the center of the Milky Way galaxy using globular clusters. But globular clusters in the halo region. Okay, last topic. So you already know there's a supermassive black hole in the center of our galaxy, kind of hiding under the bulge, the central bulge. Bless you. So these slides kind of go closer and closer into the heart of the Milky Way. Okay, so that's 200 light years in infrared. That's looking in radio emissions and kind of showing you to scale 50 light years. Okay, 10 light years and 1 light year. So the arrows are pointing to something, and it's on a later slide coming up, called Sagittarius A star. I'm a Sagittarius. Anybody else a Sagittarius in here? Okay. He's the archer. And actually, if you are looking at the constellation Sagittarius, you are looking at the center of our galaxy. The Milky Way goes through the constellation Sagittarius, and the center of our galaxy is right there. So Sagittarius A star is the black hole in the center of our galaxy. Does it look like a black hole? No. Okay. So the reason we know Sagittarius A star, again, the reason they call it Sagittarius is because it's in the constellation Sagittarius. I'm going to turn the lights back on because there's no more real pretty pictures. Ready? Okay. The reason they call it, it's in the constellation Sagittarius. The reason we know it's a black hole is by studying the movement of stars in its vicinity. Now, to me, I'm like, really? You can actually see stars? Yeah, really good telescope, right? But I'm going to show you this little video where each of these lines is a star that's moving, okay, over years, okay? And we watch how this mass, that's our black hole, affects its movement. Okay, remember, if you can find motion, gravitational influence, okay, you can get to the mass of that object. So we can. And if you know the volume, you can come up with a density and know which of these 3 versions it is. Is it a black hole because of its density? And it is. Let's see if it's on the next slide. Oh, yeah, sorry. So on this slide, it says you, what is the mass of that object? It is 3 million times the mass of our sun in a small space. So it's got to be a black hole. Where is, oh, I guess I'm going to go back one more slide. Previous slide must have done. Now, I'm not going to do the 20 minutes, but I am going to go back one slide. Like maybe a year ago, I lose track of time, 8 months ago, did you ever hear that our black hole is feeding? Yeah, it is there, I don't know. And so there'll be some energy as that stuff goes kind of in an accretion disk and is pulled apart. I do want to go back right. Is this a video? It's a short video. Don't blink. Well, I mean, you can blink, really. I got too much stuff open again. It's 12 seconds, really. I said don't blink.
Yeah, don't blink.
I know. Is it 10 years? Well, it's 1995. Isn't that cool? And as the stars get closer, they come back around. I guess that's just 5 years. Like 15. Was it 95 to 2010? One more time, people.
Can you show it again?
Yeah. Replay.
They're kind of like looping around it,
Mm-hmm.
or shooting it back away.
Mm-hmm. You know, again, I can't do the math, but somebody can do the math. You know, the laws of physics allow you to calculate the mass of that object. Very good. So this chapter will be due both 2 chapters will be due next time we meet. Very good. And I'll try to get the review sheet out so you can print it off, but I'll have some available at 4 also.